Let's talk about gravity. And with it, some people see our first baby steps into stars and astrophysics and that side of this module. For me, this is still a part of the Newtonian world because gravity acts everywhere. And all we're going to do in this book, it's nice and short, is upgrade what we already know about gravity. So gravity is something that you're already very familiar with. It's what keeps you glued to the earth and it gives you your weight. It gives us that number G, and we'll have a look at G in the next video, what that means, where it comes from. You're also familiar that at all points on the Earth's surface, the effects of gravity are pretty much the same. And that's true whether you're in Northwich or New York or Sunderland. The only problem with that is that in reality, say if I were to zoom out, well, the Earth is round and the gravitational field always points towards its centre. Before we go into what gravitation is, we want to just talk briefly about fields and field lines, and most importantly about the distinction between those two types of field. The one which is uniform, and hence called a uniform field, and the one which takes into account that circular property which we call a radial field. So let's look at uniform fields to start off with. Around me here, I am in a uniform section of gravitational field. Over my kitchen table here, the gravitational field strength and the gravitational field is uniform. So if I were to sketch this using field lines, the field lines would be equally spaced and they would all act in the same direction. That is what a uniform field is, and that's so important that I'm going to treat this like a definition that you must learn. What is a uniform field? Explain what is meant by, describe, draw a uniform field. Those are all valid types of questions that could come up. And if any of them do, well, all you need to know is that the field lines are equally spaced and they all point in the same direction. Easy. What's that telling us? Well, the spacing of the field lines has to do with the strength of the field. If all of a sudden we bunched them together, but then they were far apart over here, then this part of the field will be much stronger than this. That's what field lines are trying to show. The more field lines we have, the stronger the field. I feel a bit silly saying it, but obviously the arrows show you the direction of the field. Duh. And because it's gravity, it will always be towards the ground. Make sense so far? Uniform fields, all the field lines point in the same direction and they're equally spaced, they're parallel. That model is fine and it works on most scales that we're used to dealing with. But obviously if we're looking beyond Earth, the field isn't a uniform field. The Earth is a sphere and so it has a radial field. Take a look at the picture of a radial field. And what do you notice about it? A radial field, the lines all converge on the centre of mass. They all point towards the centre of mass of the object. At the surface, the field lines are equally spaced at that radius. But what happens to the spacing as you move away from the surface? The field lines for radial fields are divergent. They just become more spread out. If I draw a line pointing towards the centre of mass and another one next to it, then as I move away from the centre of mass, those two lines just naturally become further apart. And as I said, the spacing of field lines is an indication of field strength. So we can see that in reality, as you well know already, the Earth's gravitational field, or any radial gravitational field, gets weaker with distance from the object. So we can see that if we're comparing Northwich and New York and obviously Sunderland as well, we can see that at the surface those field lines are equally spaced and they all do point towards the centre of mass. But we can see that because the field lines spread out and diverge from that centre of mass, the strength decreases with radius. So remember, a uniform field is one where we have equal spacing of field lines at all times and they all point in the same direction. Contrast that with what you've got in front of you now. A radial field, the lines all converge on the centre of mass, they all point towards the centre of mass of the object, which means that the distance between those field lines increases as you get further away from the object, and so the field strength decreases too. The distinction between uniform and radial fields is really important because it doesn't just apply to gravitation. When we're talking about gravity and we're doing a projectile motion calculation, we're assuming it's a uniform field, and we might need to now make some comment on that. But if we're dealing with something going into space and a satellite, we're then dealing with the radial field, and we might have to make comment on that. But when we look at other types of field as well, for example the electric field around a point charge, that is a radial field. But the electric field between capacitor plates is a uniform field. And so the idea of uniform and radial fields is not unique to gravitation, and that's why it's a useful thing to learn now. So bear in mind, uniform radial fields really useful for more than just gravitation. I mean, it's a feature of any field. Any field could be radial, any field could be uniform. How do you calculate the gravitational force between two objects? Well, you need to know their mass, because gravity is the force that acts between masses, and as we've just seen, it will depend on radius as well. Isaac Newton coined it in his law of gravitation, so this is Newton's law of gravitation, important definition. The gravitational force exerted on one object due to the other is proportional to the product of their masses and inversely proportional to the distance between their centres of mass squared. Look at that again. It's proportional to the product of their masses, big M times little m. And it's inversely proportional to the distance between their centres of mass squared. It's important that we say between centres of mass. That is what a lot of people forget. Again, remember, if I was writing this on the board in real life, I would be underlining that and saying, make sure you remember between the centres of mass. Because if you say from the surface, that's not correct. The field lines don't converge on the surface of the object. The field lines converge on the centre of mass of those objects. So it's important to remember that in Newton's law of gravitation, the distance is the distance between their centres of mass squared. This sometimes means we have to add on things like the radius of our planet, but you'll see that done in the back of the book questions. Obviously this leads to an equation, and it's one that you may have seen before. The force equals minus G, which is the gravitational constant. It's a capital G. So gravitational constant 6.67 times 10 to minus 11. Capital M, little m, that's the product of their masses, divided by r squared, that's the distance between the centres of mass squared. So if you ever forget what Newton's law of gravitation is in words, look at that equation. It tells you the force acting on an object is proportional to the product of their masses and inversely proportional to the distance between the centres of mass squared. It's almost as if the equation and the law are one and the same. Why is there a minus sign? Well, r, the radius, is outwards from the object. The minus sign means that the force is not in that direction, but in the opposite direction. The minus, as far as you need to be aware, is there because it makes the force attractive. Really, why is it there? It's there because whoever wrote the spec didn't actually appreciate why that negative sign should be there in the first place. It's to do with unit vectors, but specialists don't write the A-level specification. Now I know a lot of people will say, but Rob, that minus sign means that a lot of the time my answers come out negative and I don't want them to be negative. And my answer to that is yes, I know. It's because this part of the spec probably wasn't the best thought through by the people that were writing it. And it's one of those where whenever you see it in an exam, the mark scheme says ignore sine anyway, and then they'll ask a separate question about what direction it should be going in. Honestly, it means it's attractive, and that's one of the standard answers. When you're doing maths, just make sure that you're clear, and then show the examiner that you're clear on what direction that F should be acting in. So gravitational constant, 6.67 times 10 to minus 11. It does have units as well. The units of G are Newton metre squared per kilogram squared. There's a little task in the book there to get you to derive the units in order to make that homogeneous. But again, because this is in your formula book, if you forget, just look it up. The units are there with the number 6.67 times 10 to minus 11. This formula is so easy to use. Again, it's just a plug in the numbers kind of equation. They could get you to find R, they could get you to find F, one of the M's. You know, you could plot a graph of something and come out with a gravitational constant. The examples in the book there provide loads of chance for you to just explore how this equation works. Remember that as a force, it could form part of a resultant, so we might have the gravitational force minus the upthrust. Maybe there's more than one body as well. Maybe we've got the moon applying a force that way, and then we've got the earth applying a force that way, and we might see which way our object's going to move. Again, all of these things could apply. It's a force, so expect to be doing some mechanics calculations using F equals GMM over R squared in the back of your book. But that's it for gravitation. Try this little exercise at the end, do the exercises in the book, and a very, very short video later in the week on gravitational field strength G.